Welcome to this video. My name is Phil and I am a senior lecturer in astrophysics at the University of Lincoln, which is in England. And in this video, I wanted to have a look at a specific type of orbital resonance, which is known as a Laplace resonance. Now, before we look at that specific case, let's just recap what a orbital resonance is. Well, these occur when you've got the periods of two orbiting objects that have some simple numerical relationship. So, for example, if you've got two moons orbiting a planet, it might be that one moon orbits twice for every one orbit of another one. So that's your simple numerical relationship there, basically. And because they likely will pass each other at the same point on their orbit, you get a resonance occurring, and that kind of builds up compared to if it wasn't a resonance, because they'd actually pass each other at different locations on their orbit. So it can be to do with their orbits. So let's say you've got two objects here. Let's take example two moons of Jupiter. It could be that those two orbits are some ratio of each other. So Io and Europa, for example, could have like a 2-to-1 ratio. And if it's an orbit-orbit coupling, to do with their orbital periods, then it would be known as a mean motion resonance, because one would orbit twice, one would orbit once. That's just an example, really, and so that's a mean motion resonance. But it can also occur with the spin and orbit coupling as well. So it doesn't have to be the orbital period between two objects. It can relate to the rotation of the object and its orbital period. Now, I've shown Jupiter here and one of its moons, but actually a good example is our moon and its orbit. So it takes one orbital period to do one full rotation on its axis. So that has a spin-orbit coupling. It's tidally locked, basically, which means the same face always faces towards us. So you can get those sorts of coupling occurring. And a similar other one is Mercury. That has a spin-orbit coupling. So its rotation is some ratio of its actual orbital period. So you can get those two occurring here, but the Laplace one we're interested in is actually to do with the orbit-orbit coupling instead. So things like the 2-to-1 mean motion resonance are stronger. They're known as like a first order mean motion resonance, and they're going to be stronger than like a second order one, which is like a 5-to-3. So a 2-to-1 would mean that the inner moon orbits twice for every one orbit of the outer one. Now, because objects on smaller orbits have a higher orbital velocity, they also have a shorter distance to travel. Actually, they have shorter orbital periods. So as you get further out, the orbital periods are going to get longer. And if you separate them at certain distances, then you get these orbital resonances occurring. But the 2-to-1 is going to be stronger than something like a 5-to-3. So a 5-to-3, the inner one would orbit 5 times for every 3 orbits of the outer one. And that's not quite as significant. But anyway, the specific case of the Laplace resonances is where you've got pairs of resonances occurring in a system. So a good example here is Jupiter and the Galilean moons. Now, there's actually 4 Galilean moons. You've got Io, Europa, Ganymede, and Callisto, but Callisto is not part of this resonance chain, so it's just Io, Europa, and Ganymede. Now, Io does 4 orbits for every 1 orbit of Ganymede, and Europa does 2 orbits for every one of Ganymede. So it's actually known as a 4-to-1, because Io goes around 4 times, Europa goes around twice, Ganymede goes around once in the same time frame. So this is your pairs, or this resonant chain, basically, or pairs of resonances. And this is a Laplace resonance. And it's not the only one. This is an easy one to see, actually. You can actually look at this yourself with your own telescope. But there are exoplanets that have the same Laplace resonance as well. So this is an exoplanet system. It has 4 planets in, and the 3 outer ones are in a 4-to-1 Laplace resonance as well. So it's actually the same as the Galilean moons. The inner one, D, is not part of the resonance chain. So you've got the pairs between C and B, B and E, and then obviously C and E as well. And you'll notice that the lettering of these planets here is not in order. It's not in alphabetical order from the center out. And the reason for that is the lettering comes from when they were discovered. So B would have been discovered first, and then C, and then so on, basically. And the bigger ones typically get discovered first because they're easier to see. So it doesn't necessarily mean that it's from the position in their orbit around the actual star. So that's another example of a Laplace resonance around an exoplanet system. And another good one actually is Trapis I. Now this has 7 terrestrial planets that are in and around the habitable zone. It also orbits a small red dwarf star, but they're quite a tight resonance chain system. Basically, it's like a Laplace resonance chain, and from the inner one to the outer one, you've got a 8:5 ratio. So the inner one will go around 8 times for 5 times of the next one, and then it goes 5:3, 3:2, 3:2, 4:3, and then 3:2. So you've got this really long and quite tight resonance chain in this particular system. And this is interesting because, well, these are all terrestrial planets essentially, and they are in and around the habitable zone. Again, another interesting thing about this system. So these resonance chains, or these Laplace resonances, do occur in quite a few different sorts of systems. So thank you for watching, and if you enjoy, then check out some of the other videos.